Assalamu alaikum everyone, welcome to the course of Real-Time Embedded System. Today we will start another chapter from the book of Wine Wolf, and in this chapter we are going to cover the program design and analysis of embedded system. So in this chapter we will study some useful components of embedded software, models of programs such as data flow, control flow graph, and introduction to compilation methods, analyzing and optimizing programs for performance, size, and power consumption, how to test program for correctness, and finally at the end we will look into the software model. So let's start this topic. So in this slide we will talk about the additional requirements of embedded softwares. Most of the time the basic functionality or the basic goal of embedded software is to provide the basic functionality. Often we require to meet deadlines. We want the program to fit in the limited memory and meet consumption requirements, power consumption requirements. We can use assembly language to write program. We can also shift to high-level languages which are mostly used nowadays. We have C, in which we write procedural statements. We have C++, that is object oriented, and Java, that is object oriented. So we can do all sort of high-level programming in these languages. Furthermore, we can use real-time operating systems, for example Windows, and all these can aid in the building of embedded system software. So when designing a program or analysis, it must go through these steps: software components, representation of programs, assembly, and linking. We are going to look into these one by one in detail. So first start with the software components, which we also known as components of embedded programs. There are three structures or components that are commonly used in embedded software: the state machine, the circular buffer, and queue. State machines are well suited for reactive systems such as user interfaces. Buffers, queues are useful in digital processing. So let's move on to the next slide. So as I've already told you in previous slide that software state machines keep internal state as variable, changes state based on inputs. So there are variables and the state are changes on the basis of inputs. And the uses of this state machine is reactive system, where we get some sort of reaction from a user and then we do something. So state machine, when inputs appear randomly rather than periodic samples. So that's why we use state machine when input appear randomly rather than periodic sample. It's often convenient to think of the system as reacting to those inputs. The reaction of most systems can be characterized in terms of input received and the current state of the system. This loads naturally to finite state machine style of describing the reactive system behavior. Moreover, the behavior is specified in a way it is natural to write the program. Implementing that behavior in a state machine style, the state machine type of programming is also an efficient implementation of such computation. So finite state machines are first encountered in the context of hardware. So the behavior we want to implement is a simple seat belt controller. So let's move on to next slide and see how it works. So this is the example of simple seat belt controller. Here we have input, outputs, and the dash that you see here, it means no action. And this ideal state is in force when there is no person is on the seat, and when there is a person on the seat, it will change its state from ideal to seated. And when it's seated, the timer will on, and no belt and no timer. If it's seated and there is no belt and no timer, we will do nothing. So if a person is seated and the time has gone, So timer on and buzzer, it will go to the buzzer state. So if it is in buzzer state and the next state is that it goes to idle, so it means that we need to buzzer off and no seat. Okay, so if it is in buzzer state and belt is on, so it means that it is going to next state, that is belt, buzzer will be off. From belted state it can go to seated state, no belt, so the timer will on. Okay, and from seated state if it comes to the belted state, it means that we have fastened the belt, so we do not require any action, so that's why we have a dash here. Okay, so if it's in belted state and then it goes off, like it gets out of the seat, then it comes to idle seat, no seat, it means no action is required. Okay, so this is the behavior of simple seatbelt controller. The controller job is to turn on the buzzer if a person sits in a seat and does not fasten the seatbelt within a fixed amount of time. The system has 3 input and 1 output. The 3 inputs are sensor of the seat to know when a person sits down, a seatbelt sensor when the seatbelt is fastened, and a timer that goes off when required interval has elapsed. The output is buzzer. The ideal state is force when there is no person on the seat. When the person sits down, the system goes to seated state and turn on the timer. If the timer goes off before the seat belt is fastened, okay, the machine goes to buzzer state. If seat belt goes on first, it enters belted state. So if before the buzzer turns off, we fasten the seat belt, we will move to this state, belted. If the buzzer goes off and we haven't fastened the seat belt, it will go to buzzer. If the seat belt goes on first, it enters the belted state. When person leaves the seat, the system goes back. When the person leaves the seat, it goes to idle. So it can go from buzzer to idle, it can go from belted to idle. To write C behavior, we have loaded current values of all the 3 inputs. So what are the inputs here? We have seat, we have belt, and we have timer. So these are all the 3 inputs which we need to write into variable. And similarly, hold output in variable. What are the outputs here? We have we have buzzer output and we have timer on output. So we have 2 outputs here, timer on and buzzer. We used variable named state to hold current state of the machine. So we will use variable state to hold the current state. The current state can be idle, seated, belted, or buzzer. And then we will check at the input. What's the input? Like, is it the seat input, it's the belt input, or it's the timer input? And then we will do some appropriate action. So we use variable name state to hold current state of machine and switch statement to determine what action to be taken in each state. So let's move on to the algorithm of this finite state machine. So this C codes take advantage of the fact that state will remain the same unless explicitly changed, thus makes self loop back to same state easy implementation. The state machine may be executed forever in a while loop or periodically called by some other code. In either case, code must be executed regularly so that it can check current state value of input and if necessary go to next state. So these are all the states that we have defined earlier. Ideal, that is the starting state, seated, belted, and buzzer, and we have assigned the number like the orderly number. So this is our state. So switch state. If the case is idle and if seat it means that the person is on the seat. The next state will be seated and timer will be on is equal to true. So this is our first case. In the second case, because we were seated in the previous state, so next will be seated. Okay, case seated. Now in case seated, we have seen in previous figure that the next state is belt. So if belt state is equal to belted, we will go to next state, that is belted. If not, we will go to timer. Okay, so else if timer, so state is equal to buzzer. We can go to two direction. Either we can go to belted from seated, or we can go to buzzer from timer. So it depends on whether the person has fastened the seat belt within the desired time interval or not. And after that we will have another case that is of belted, and finally we'll have another case that is of buzzer. Okay, so there are few cases that are missed here, but the purpose is to just let you know that we are going from one state to another state, and we check the input first. For example, if seated, from sensor; if belted, from sensor; if timer, from the sensor. Then we move on to the next state. Okay, so if you want to look at the complete code, you can go into the book and see that code. I have shared the book on the portal as well as on your MS Teams. So let's move on to next slide. So in this slide we are going to talk about signal processing and circular buffers. The circular buffer is a data structure that lets us handle streaming data in an efficient way. At each point in time, the algorithm needs a subset of data stream, but forms a window into a stream. So we form a window into a stream. Now the window slides with time as we throw out old values. No longer needed, add new values. So the window just acts like a slide. So we have a sliding window and we will throw out the old values that are no longer required, and we will add new values. Since the size of window does not change, we can use fixed size buffer. So we can use fixed size buffer to hold current data. But to avoid constantly copying data within the buffer, we will move head of the buffer in time. So what we are going to do, we are going to use the head to move into time. The buffer points to the location at which next sample will be placed. Every time we add a sample, we automatically override the oldest sample, which is the one that needs to be thrown out. When the pointer gets to the end of the buffer, it wraps around the top. So let's check the example of this. As I've told you, it is commonly used in signal processing. New data constantly arrive. Each data has limited time frame, lifetime. So for example, this data, it has limited time, this data has limited time. So D1, D2, D3, D4, D5, D6, D7, these are all data frames. What we are going to do, we are going to form a window first. Okay, so for example, this window can hold 4 data items, and then we have to move that window. So rather than doing that, what we can do, we can define a buffer. So use a circular buffer to hold the data stream. So let's check it out how it works. So this is our window in time frame t, and this is our time frame t plus 1. So these are two windows. So you can see that we have left now thrown the old data sample, that is d1, and we are shifted to d2, d3, d4 and d5. So what we will do, so this is the example of circular buffer. We have x1, x2, x3, x4, x5, and this is our data stream. This is our data stream, as you can see, and this is our circular buffer. So our circular buffer has just 4 locations. So we will have x1, x2, x3 and x4. And what will happen next? So this is our time frame 1, this is our time frame 2, and this is our time frame 3. Okay, so at time frame 3 you can see that we have thrown out the values of x1 and x2. But why do we call it circular buffer? So let's take a look. So what will happen is a circular buffer. So initially we have thrown out the value of x1. So the next value will come in and replace. The rest of the thing will remain same. We do not need to copy each item again and again. And next time in stamp 3, what we will do, we will throw out x2. So this x2 will be thrown out. So see what will happen. We have x3. And next, if we want to throw out, what will throw out? X3 and x7 will come. However, we do not have x7, so we will not go further. So this is the circular buffer. We are just throwing out the old data and we are moving just the new data. So what actually we are doing? We are moving the head of the buffer in time. We are moving the head of the buffer in time. So that was about the circular buffer. So we have x7. So in this slide we are going to talk about the queues, which is the third most important component of embedded software. So previously we talked about state machines, we talked about circular buffer. So queues are basically kind of a buffer, but that is elastic buffer. It holds data that arrives irregularly. Queues are also used in signal processing and event processing. Queues are used whenever data may arrive and depart at somewhat unpredictable time, or when amount of data may arrive. So we have like amount of data, variable amount of data may arrive. A queue is often referred to as elastic buffer, as I've told you. One way to build a queue is with linked list. So one way we can build it with using linked list. The approach allows the queue to grow to an arbitrary size. But in many applications, we are willing to pay the price of dynamically allocating memory. So if we use linked list, you are going to increase the size of the linked list arbitrarily, which will result in price. So another way to design a queue is to use an array that is like fixed size to hold all the data. So the first step in designing a queue is to declare the array that we will use for the buffer. So let's go to the example and see how the queues, elastic queues works. So this is the example of elastic buffer or queues. So we have a C code and we are going to put the values into the queue and take out the values from the queue, and it's like a kind of a fixed size queue. We are not going to use linked list because of the price overhead and because of the arbitrary increase in the size. So first step in designing the queue is to declare the array that we will use for buffer. So here in first statement, if you see, we have defined the size of the array. In the second, that's the maximum index value in the queue max, and then we have finally defined our array of q, that is q, and that's the maximum size. And then these two variables are to keep track of the state of the queue, and this is I say is the increment. When we are going to add the values into the queue, so we need to increment, and when we need to remove the values, we need to decrement. Okay, so when we add the value, we will increment the tail. When we remove the value, we are going to decrement the head. Okay, so as our initialization code shows, we initialize head and tail to the same point. So you can see head is equal to 0, tail is equal to 0, increment is equal to 0. So this is the code where we need to void enqueue. It means that we are going to add data to the queue. So when we add data to queue, the increment, we need to increment the tail, and when we remove data from the queue, we need to decrement the head. Okay, so if you see, this is the code from void enqueue. This is the function. So this is for adding data to the queue, whereas int dequeue, it is getting data out of the queue. So if IC equal queue size, it means it is kind of a full. Okay, because the increment has reaches to the queue size that is the maximum size, we will generate an error. Okay, otherwise if it is not full, what we will do, we will go to the tail in queue and put the value that we have to put in the queue, and finally after putting the value we will increment the tail. So IC plus plus, so that IC plus plus means we have incremented tail. If tail equal to Q max, so if tail is like reaching the maximum, we will put tail is equal to 0 and we will increment the tail. Okay, if this statement is true, we will put tail is equal to 0, so we'll move to the base. Otherwise we can increment the tail. Okay, so likewise in DQ, when we are going to get the value out of the queue, we are not adding any value. So this is just the variable that we have defined in which our result will come. So we are checking if IC equal to 0. So because we are in the case of head, we need to check if it's already empty. Here we were checking if it's already full. So here we are checking if it's empty, we will error. If it is not, we will put head in queue. Queue is basically the queue and head is basically the variable. Okay, so whatever value we'll get here, we'll put it in return variable, and then we will in decrement, because we have taken out the values. Now we'll go down, we will need to go down. If head equal q max, it means that head was pointing at the maximum. Okay, what we will do, we'll put head is equal to 0, so that head will go down, else head plus plus, otherwise we will do head plus plus, we will increment the head, return value, and we will return the value of the value that we get from the here. After return value is equal to q, the value we get from here, we will return it. So in this slide we are going to talk about the models of program. We develop model of program that are more general than source code. Why not use source code? The question arises. First, there are many different types of source code, assembly language, C code, and so on. But we can use a single model to describe all the source code once. We have such a model, we can perform many useful analysis on the model more easily we could do on the source code. So source code is not a good representation of program. It is clumsy, leaves much information implicit, and compiler derive intermediate representation to manipulate and optimize the program. So our fundamental model for program is the control data flowgram. So our fundamental model of the program is CDFG, which we are going to see in the next slide. So as I've told you previously, our fundamental model for program is the control data flow graph. We can also model hardware behavior with CDFG. Now to understand CDFG, we start with pure data description and then extend the model to control. So here we are just going to study DFG. Once we are done with the DFG, we will extend it to CDFG. Now, a data flow graph is the model of program with no conditions. In a high-level programming language, a code segment with no condition. It is more precisely saying one entry point and only one exit point. And this is known as basic block. So basic block in the code has one entry point and one exit point. As the code is executed, we would enter the basic block at the beginning and execute the statement. Before we are able to draw the data flow graph for the code, we need to modify it slightly. There are two assignments to the variable, so let's go and check out the example. So if you see in this block, basic blocks, the original basic block has two assignments to x. So it appears twice on the left side of an assignment. Here you can see that it has two assignments. X is equal to a minus c and x is equal to a plus c. We need to rewrite the code in a single assignment form. So this is a single assignment form. So W is never getting affected, x1 is never getting affected, y is never getting affected, x2 is never getting affected. Here we were losing the value of a minus c. So this is single assignment form of basic block. Since our segment specification is C code, we assume that statements are executed sequentially so that any use of variable refer to its latest assigned value. So we will have latest assigned value. X2 will not be updated because we are using single statement. The single assignment form is implemented because it allows us to identify a unique location in the code. So X2 identify unique location, Y identify unique location. However, in original basic block, X was here and X was here, so we cannot uniquely identify the location. As an introduction, we use two types of node in graph. Node denotes operation and square nodes denotes values. So let's check out the graph, the data flow graph of this single assignment form. So this is the final form of data flow graph, and that is the refined form. We are not using any square here. Otherwise, we can put A, B, C, D all in square because these are all the values. So we need to put all the values in square, but for simplicity, like for the refinement, we do not use squares here. Rather, we are using the operations. So these round nodes, this plus, this plus, this minus, this plus, and this plus, these round nodes are representing operations. So if you see here, a plus b is equal to w, so a and b is coming from here. A plus b is equal to w. So this is w. How we are getting x2? This is a plus c, we are getting x2. And then how we are getting this x1? This is a minus c. So this is the data flow graph, and from x2 we can uniquely identify the location in the block. So x2, I can see x2 is here. So this is a block, okay? This is again a block, this is again a block, this is again a block. So all these are blocks. So let's move on to next slide. So data flow graphs and partial orders. So as I've told you, this is the standard data flow graph. If you go to the book, you can see the extended data flow graphs. In extended data flow graphs, we will have square at A, B, C, D, and E. These are all the variables. All the variables are in the square. However, we are not using any square here. This is the standard data flow graphs. So we have seen that we have simplified our assignment. If you go to the original basic block, we were having two assignments to x. Okay, so what we did one single assignment. So can reorder operation like the way we can reorder operations. So reordering the operation means that the next operation might not need to wait for the first operation to complete. So ultimately it will result in reduced pipeline conflict. You already know that in pipelining we have, like, one thing is, like, for example, if one instruction is being getting decode, the other one is getting fetch. So like the way, if we are computing x and x is needed at some other point, there will be conflict and our system will stop and we will have high memory latency. So we do not like high memory latency by doing reordering of the operations. Okay, so we can speed up our system, we can speed up our program, and all that can be done with the help of ordering operations. As I've told you, single assignment form means that data flow graph is cyclic. It's a acyclic graph. You won't see any cycles here. If we assign x multiple times, if we have assigned x multiple times, then the second assignment would form a cycle. So we haven't assigned x multiple times, that's why there is no cycle in the graph, including x and operator to compute x. Keeping data graph flow acyclic is important in many type of analysis we do on our graphs. So it is very necessary to keep the data flow graph acyclic so that we can perform all the analysis easily. Otherwise, if we have cycles here, it will be very difficult for you to uniquely identify each location of the variable. So that was it for today's. Next time we'll continue our remaining control data flow graph.